Chapter 5 Chemical Kinetics Part 3. For the red laws, look at this homogeneous fraction. So for the red is equal to the K for the constant, and this is the concentration of A, and they have the exponents M here, and the concentration of B for the reactant, and this is the exponent of N. Red law or red expression, M and N are exponents found experimentally, so no necessary connection between the stoichiometry of the coefficients alpha and beta and red exponents for M and N. Usually small integer, sometimes simple fractions or zero. Red laws. This is the red, K is a red constant, and when you look at this, K depends on T, and must specify T at which you obtain K, and this is the red because it's negative of reactant, and this is the time, and this is the red of K, is the concentration of A and B with the exponent M and N. So when you look at this, the red law for the reaction 2A plus B produce the 3C, and this is the rate. A and B is the 0.2 molar for A, and B is 0.3 molar. And we use this formula, and then you get the rate is 0.003 molar per second. This is the rate for the K, A, B with the exponent M and N. So exponents specify the order of fraction with respect to each reactant. Order of fraction, look at this, M is equal to 1. So this is the first order. If M is equal to 2, second order. If M is equal to 3, is third order. And if 0 is the zero order. And this means it does not affect red. Overall order of reaction, you need to sum of orders M and N of each reactant in red law. So this is the example. We look at the first order for this X and the first order for Y, and this is the second order too. So just overall order is you need to sum for the X, Y, and Z for this exponent. So it's equal to 4. So this is the fourth order. Determining order of fractions. So look at this. Rate second order for this concentration hydrogen iodide. And this is the second order overall because only one reactant here. Sometimes N and M are coincidentally the same as stoichiometric coefficients. Actually, how you get the second order for the reaction? We will look after this how to calculate the exponent and also the K. And this is how to calculate K from red law. If we know red and concentrations, can use red law to calculate K. So from example 2 at 508 degrees Celsius, so rate is equal to the 2.5 exponential negative 4 molar per second. So this is the concentration of hydrogen iodide, 0.0558 molar. So this is the rate. And then you use this formula to find the K. And how to determine exponents in red law? Experiments, method of initial rate. If reaction is sufficiently low or have very fast technique, can measure the concentration of A versus time at very beginning of reaction before it slows very much, then this is the initial rate. so negative because direction, and this is the change of concentration divided by the change of time. Set up series of experiments where initial concentrations vary. Look at this example. Method of initial rates. So this is the equation. And we have the experiment 1, 2, and 3. So this is the concentration of A and B. And this is the initial rate. Convenient to set up experiments so the concentration of one species is double or triple, and the concentration of all other species are held constant. Tells us effect of concentration varied species on initial rate, reaction order, and rate. So if you look at this, for the first order, this is doubles the rate. If reaction is second order, quadruples the rate, and if the reaction is a zero order, so rate does not change. And this is how you identify the reaction order and rate. Look at this example. This is the experiment 1, 2, and 3, and this is the concentration, and this is the initial rate. And comparing the experiment 1 and 2, look at this, 1 and 2, and look at this for the rate 2, you divide by the rate 1. So here, 2, you divide by rate 1, and you get 4 here. And 4 is equal to the, just now is the rate 2. Look at the experiment 2. For the rate 2, this is the rate 2. And for the rate 1, so this is the rate 1. We look at the exponent m and n. Okay, when we look at this, we look at the 1 and 2 for the B concentration, same, 0.1 molar. And you can find the exponent of m. And look at this, m is 2. Okay, and if you want to find the n, use the same formula to find the exponent n. This is how you identify the exponent n. You comparing the experiment 2 and 3. Look at this, the concentration of A, similar, same, 0.2. And the difference is the concentration of B. So you can find the exponent n. And you divide the rate 3 divided by the rate 2 for the initial rate, and you get the 1 here. And you can find the n is equal to 0. So for the method of initial rate, conclusion rate, we can find the k, our exponent m here is 2, and this is the concentration of A, exponent 2 here. Can use data from any experiment to determine k. Let's choose first experiment. So we choose the rate 1 here and divide by the concentration of A, and you get the rate. So meaning that you can use data from any experiment to determine the value of k. This is another example. So this is the rate for the reactant SO2, and this is the O2, and this is the exponent m and n, and this is the data, and this is the initial rate. You compare experiment 1 and 2. If you look at this experiment 1 and 2, so they have the same for the concentration of oxygen. So meaning that you can find the exponent m. If you compare experiment 1 and 2, so you get the m is equal to 2. And how you get the exponent n? You comparing the experiment 2 and 4. 2 and 4, because they have the same concentration of A for the experiment 2 and 4, and then you can find the exponent n and use the formula, and you get the n is equal to 1, and this is the rate after you identify the value of m and n. So the first order in the O2 for the oxygen, and the second order in the sulfur dioxide, and the third order for overall, because 2 plus 1, and you get the 3. You can use any experiment to find the value of K. So you just choose the red one, 2, 3 or 4, and you get the same K. This is another example for method of initial rates. So we look at this experiment 1, 2, 3 and 4. So this is the red. So you can look at this, how to compare. So this is the overall order. You get the 4. And let's continue part 4 in chapter 5, Chemical Kinetics. So concentration and time. So we know rate law tells us how speed of reaction varies with concentrations. Sometimes want to know concentrations of reactants and products at given time during reaction. How long for the concentration of reactions to drop below some minimum optimal value need dependence of rate on time. Integrated rate law for first order reactions, and this is the first order, and for the first, second or zero order, for this part you just remember the formula and we do the exercise or tutorial, and then you can understand of that. And this is for the second order, and look at this exponent 2. And this is the formula. How to determine reaction order using graph. So you need to make 2 plots, 1 and 2 here. And when you look at the half-lives for first order reactions, and this is the half-life for the first order reactions, and this is the still for the first order reactions, and this is the first for the second and the third, and this is the half-life graph, and this is the example when using the half-life. For the second order, so this is for the zero order reaction. So for the zero order, directly proportional to initial reactant concentration. Potential energy diagram. So this is the activation energy. This is the exothermic reaction. So the enthalpy is negative. For the exothermic, actually for the exo and endo, we already discussed in the chapter 1 and 2. This is the transition state or activated complex. So this is the summary of the kinetics. We look at the zero order, first order and second order. So this is the rate law, integrated rate law, and this is the half-life. We look at the half-life. This is for the zero order, and this is for the first order, and this is for the second order.